Good morning everyone. In today's class we are going to discuss examples of photophysical unimolecular reactions. The first example is decomposition of hydrogen iodide. So already we know this hydrogen iodide in presence of light decompose to form hydrogen and iodine. The mechanism involved in this particular process is, in a first step, hydrogen iodide absorbs a light and undergoes homolytic cleavage and form hydrogen and iodine free radical. Now the first step will be an excitation process where after absorbing the radiation, HI molecule get excited followed with dissociation into these free radicals, and that is the reason why the rate of the reaction of this particular step is entirely depending on intensity of incident radiation, that is I naught. Let us consider K1 is a rate constant and the rate of a first step is equal to I naught, that is intensity of incident radiation, into rate constant. Now since we got these free radicals, hydrogen free radical and iodide free radical, these free radicals are highly unstable. So hydrogen free radical in a second step reacts with stable hydrogen iodide molecule to form hydrogen and iodide free radical. Let us consider K2 is a rate constant of the second step, and the second step is exothermic in nature, so heat is given out. So it is more feasible because according to thermodynamics, when delta H is negative, it is spontaneous process, it is more feasible. Now these iodine free radical obtained, it reacts together to form iodine. This is the third step, and a fourth step is there is also possibility that these iodine free radical interact with HI to form hydrogen free radical with the liberation of iodine molecule. But this particular process is a non-spontaneous because delta H in this particular process is positive, that is the reaction is endothermic in nature. Generally we do not consider such reactions because of their less feasibility. Now let us apply steady state principle and the rate law. If we apply the rate law for the decomposition of HI, if we observe in this equation, equation 1 and equation 2 is involving dissociation of HI. Fourth equations we are not considering because it is endothermic in nature. Therefore, rate law for decomposition of HI is equal to K1 into I naught plus K2 into concentration of reactant, that is H dot concentration and HI concentration. Let me call this as equation 1. As we can observe in equation 1, we are having hydrogen free radical. So using steady state principle, we will try to calculate hydrogen free radical. So now by steady state approximation, for an intermediate hydrogen radical concentration, we know that rate of intermediate is equal to 0. You can observe in a first step hydrogen free radical is formed, and in a second step that hydrogen free radical got consumed. Okay, so therefore since in a first step hydrogen free radical is obtained, therefore dH dot upon dt is equal to K1 into I naught, that is intensity of incident radiation, minus the negative sign indicates in a second step hydrogen free radical is consumed, so it is having a negative sign, so minus K2 into concentration of H dot into HI, and this sum is equal to 0 according to steady state approximation. Or else even we can consider the rate of formation of intermediate, that is hydrogen radical, that is K1 I naught, is equal to its decomposition, that is K2 H dot into Hi. Both the things are same. So this is our equation 2. Here I naught is intensity of incident radiation and K1, K2, K3 are rate constant of the reactions. Now I am going to substitute this particular equation 2 in equation 1. In this equation 1, you can observe K2 hydrogen free radical concentration and hydrogen iodide concentration is equal to K1 I naught. So I am just replacing now in a place of K2 H dot Hi as K1 I naught, and if I substitute here, as we can see, rate of formation of Hi is equal to K1 I naught plus K1 I naught, which is nothing but 2 times K1 I naught. Let me call equation 3. Now in this particular case, we have calculated rate of dissociation of Hi without any quenching process. So the quantum yield of this for this particular process is rate of disappearance of Hi divided by rate of absorption of light. So rate of disappearance of Hi is minus dHi upon dt, and rate of absorption of light is a rate of first step, that is K1 into I naught. From equation 3, we are going to substitute the numerator value as 2 K1 I naught and denominator is K1 I naught. Now this K1 I naught gets cancelled and we get quantum yield in this particular step is equal to 2. Here we have not considered any quenching process. Now it is observed that as the reaction proceeds, the quantum yield decreases due to accumulation of iodine. So as we can observe in these reactions, in these 4 reactions, especially in third and fourth reaction, iodine is generated. These iodine will accumulate over the reactant and as a result it decreases quantum yield. And the decrease in quantum yield is due to this particular equation where hydrogen free radical reacts with accumulated iodine to form Hi and iodine free radical. Let me consider K4 is a rate constant of this equation. Now in this particular fourth equation, hydrogen free radical is involved. So by including this reaction, once again let me apply steady state approximation for hydrogen free radical concentration. Steady state approximation for hydrogen radical concentration is dH dot concentration upon dt is equal to, in the first step hydrogen free radical is formed, so K1 into its intensity of incident radiation. In second step hydrogen free radical is consumed, so minus sign will come because here hydrogen free radical is consumed, so K2 into concentration of H dot into concentration of Hi. And as we can see in this equation 4, here also hydrogen free radical is consumed, so minus K4 hydrogen free radical into iodine free radical, and this particular algebraic sum is equal to 0. Now let me simplify this equation for hydrogen free radical. So initially I will shift both these negative terms of left hand side to right hand side, and after shifting to right hand side, let me take out hydrogen free radical concentration out. So as a result I am going to get this equation. In the next step, keeping hydrogen free radical concentration to the one side, let me shift the terms within the curly bracket to other side, and we get a molar concentration of hydrogen free radical is as shown in this particular equation. Now I will substitute that hydrogen free radicals in the equation 1. which we have derived earlier. So after substituting hydrogen free radical in this particular place, we get rate of decomposition of HI is equal to minus dHi upon dt is equal to K1 I naught as it is, K2 and HI concentration as it is. In a place of hydrogen free radical concentration, we substituted the earlier value, and after substitution, as we can observe here, in this two terms on right hand side, K1 I naught is a common, I am taking out, so within the bracket we get 1 plus K2 hydrogen iodide concentration divided by K2 into hydrogen iodide concentration plus K4 into iodine concentration. As we can observe the second term on the right hand side within the bracket, here K2 HI concentration is repeated. So let me divide numerator and denominator of this particular term by K2 and hydrogen iodide concentration. So I am going to get this equation. Further, let me shift I naught to other side and multiply this K1 with the inner bracket. We get minus dH upon dt whole divided by I naught is equal to K1 into 1 is K1 plus K1 into 1 is K1 divided by this whole term. When we observe this particular equation, we can clearly observe that molar concentration of iodine which is accumulated during this particular process is inversely proportional to quantum yield. So dH upon dt upon I naught gives us a quantum yield. So this quantum yield is inversely related to molar concentration of iodine. So based on this, we can suggest as iodine concentration increases, quantum yield decreases. So here the first quantum yield we have calculated without any quenching process, and second step we have considered a quenching with iodine molecules which gets accumulated during the process. And as we observed here in this particular equation, that as the concentration of iodine increases, quantum yield decreases, and experimentally also it is found the same, and theoretically also it is supporting for the same observations. Now let us discuss a second example, that is a dimerization of anthracene. And in our equations, let us consider capital A indicates anthracene. We know that anthracene in a benzene gets dimerized and shows fluorescence when irradiated with a light, and it is observed that the frequency of fluorescent light is less than that of light incident, and the mechanism of this particular process is shown on the screen. In a first step will be excitation, where anthracene molecule absorbs a light of energy h nu and getting excited, that is A star. Let me consider K1 as a rate constant in first step. Later on, this excited anthracene molecule colloid over a neutral anthracene molecule and undergoes dimerization and forms a dimer molecule A2. Let me consider K2 is its rate constant. As we know that excited anthracene molecule undergoes fluorescence, so in a third step these excited anthracene molecules comes to a ground state with the emission of light with a frequency nu dash, and let me consider K3 is a rate constant of this particular fluorescent process. So now in this particular case, A star, that is activated anthracene molecule, is a excited state. So now here we are going to apply steady state principle for A star concentration of the molecule, and let us consider I naught is the intensity of light absorbed. Then according to steady state principle, dA star upon dt, that is the rate of formation of anthracene activated molecule is equal to K1 I naught, because as we can observe in this equation, we come to know that in the first step anthracene activated molecule is formed, and that of second and third step which gets consumed. So the rate of formation of anthracene molecule is equal to K1 into intensity of incident radiation minus K2 into concentration of A star into A minus K3 into concentration of A star, and algebraic sum of all that is equal to 0 according to steady state principle. I will simplify this equation for molar concentration of anthracene activated molecule. So here initially I will shift both the negative terms to right hand side and become positive. Then I will take out A star concentration common. Then in a bracket I will get K2 into molar concentration of A plus K3. Then I am going to keep this molar concentration of anthracene concentration to one side and shift that values from the bracket to other side. Then I will get the molar concentration of anthracene excited state is equal to this value. Let me call this as equation 1. The anthracene undergoes dimerization. So the rate of formation of dimer, that is R, is equal to dA2 upon D2. As we know that in a second step dimerization takes place. So rate of formation of dimer is equal to K2 into A star concentration into A. So after substituting molar concentration of A star concentration from equation 1 in this rate of formation equation, we get equation 2. Let us calculate a quantum yield for formation of dimer. The quantum yield for formation of dimer is equal to number of moles of dimer formed, that is A2 formed, divided by number of Einsteins absorbed. From equation 2, the number of moles of A2 formed is given as dA2's concentration upon dt. The value of this we can get it from equation 2, which is substituted, and I naught is the number of Einsteins absorbed. Simplify, so this I naught terms get cancelled and we get quantum yield for formation of dimer A2 is this. In the next step I am going to divide numerator and denominator by K2, then I get equation number 4. As in this equation 4 there is no term I naught, so the quantum yield of formation of a dimer is independent on intensity of light absorbed, that is I naught. By looking this equation you can clearly observe that quantum yield for formation of dimer, that is A2, is independent on I naught. But as we can observe here, there are two terms, that is a molar concentration of anthracene concentration is there even in a denominator as well as numerator. So there will be a confusion now whether the concentration of anthracene is going to affect to quantum yield or no. In that particular case, let us we have to consider two different cases, whether molar concentration of anthracene is less or high. So whenever we consider anthracene concentration is very high, then K3 upon K2 will be neglected, and if we neglect K3 upon K2, then a molar concentration of A, molar concentration of K gets cancelled. And if the value of molar concentration of A is very small, then automatically molar concentration of A gets neglected, and this K3 upon K2 terms will be exist. Now let us consider two cases. A case 1, if the molar concentration of anthracene is very low, then molar concentration of anthracene is very much less compared to K3 upon K2. Then in equation 4, as the value of A is very less, we can neglect this. So the remaining term is just K3 upon K2. K3 upon K2. Simplify this, we get this particular equation. From this equation, it is clear that quantum yield for formation of dimer is directly proportional to molar concentration of anthracene. That is, quantum yield of dimer formation increases with increase in molar concentration of anthracene monomer. Okay. The second possibility is if molar concentration of A is very high. That means molar concentration of anthracene concentration is very much large compared to K3 upon K2. In that case, equation 4 becomes, in this equation 4, as the value of molar concentration of A is very large, K3 upon K2 is neglected. We get this, cancel molar concentration of A. So we get the equation that 5A2 equal to K1. Here there is no molar concentration of A term. Thus, quantum yield of formation of dimer is independent on molar concentration of anthracene. So the next one is photolysis of ammonia. So this ammonia decompose with a light whose wavelength is shorter than 210 nanometer into nitrogen, hydrogen and hydrazine. It shows a maximum absorption at 119 nanometer, and it is observed that a quantum yield at 293 Kelvin it shows 0.15, and that of at 473 Kelvin it shows 0.50. The mechanism involved in this particular process is as shown on the screen. In the first step, ammonia molecule absorbs the radiation and gets excited, and after excitation it splits into NH2 free radical and H free radical. This formed NH2 free radical and hydrogen free radical both are highly reactive. So formed NH2 free radical may react with another NH2 free radical and colloid with a quenching material present in the reaction mixture, or sometimes it is getting colloided to the wall of the container. Let us represent M, and it gets converted to N2H4, that is hydrazine. Even the reactions between two NH2 free radical generates nitrogen and hydrogen. Also, it is observed that NH2 free radical combines with hydrogen free radical and it gets back ammonia. Also, hydrazine molecules colloid over hydrogen free radical with the formation of ammonia and NH2 free radicals. The formed hydrogen free radicals will colloid to the wall of the container and gets neutralized to hydrogen molecules. So these are the different mechanisms were observed during photolysis of ammonia. The fourth reaction will be photolysis of acetone. So acetone vapors decompose by absorption of light of wavelength 313 nanometer. The products appears to be radicals. In 1947, a scientist Davis has suggested following mechanism. It is observed that the quantum efficiency of this particular process is less than 1. The rate of this photolysis of acetone is shown in this particular equation. Thank you.